Okay, second application. I said I would take a break. I didn't actually take a break, but I switched videos. Second application. Consider these two sets of points. And I would advise you may actually want to pull up the slides on the side here because I don't know to what extent the points are going to, the colors and shapes of the points are going to show up on the video. But suppose I have a data set consisting of two sets of points, set A and set B. And on this plot, I have drawn set A as being blue and round, and set B as being red and square. So there are two distinct sets of points. It's a data set that I suppose we somehow want to, we have this data set which has different characteristics, and some points are different than others. And so we've separated them out into set A and set B. And what we're getting at here, this is the application that this is drawn from is from machine learning. And I'm not going to go into the machine learning part of it, but it's something that if you've taken a course in machine learning would probably be very familiar to you. And it may well be something that if you took that course, the discussion of how these things were constructed was brought up and an optimization problem was derived, but then the course might have stopped there because it's not an optimization course. It turns out this application is one that normally, I think in a machine learning course, they would state it as a nonlinear optimization problem, as a quadratic program, not as a linear program. And there are some reasons why a quadratic program here might be a better idea. And I'll talk about those maybe in a live session. They're peculiar. And even the author, like Vanderbay, in Vanderbay's book, this application is discussed sort of as if this is an obvious linear problem and there's no need to think about the reasons why a nonlinear version might be better. In any case, it is still a problem that involves distances, and therefore we should talk about it because it is something that doesn't look very linear that we can turn into a pretty passable linear thing. And it has an interesting implication that we'll see later on nonlinear functions. So what I want to do is I have this set of blue points and red points, round points and square points, and I want to decide if there exists a single line that separates all of the blue points from the red ones. And of course, in this example, the answer is yes. But I could easily design a set of points where the answer would be no. So if I put some red square points, I don't know, all over here, and maybe one up here, maybe one down here, maybe you can satisfy yourself that there is nowhere I could draw a line such that all the blue points are on one side and all the red points are on the other. The red points sort of surround the blue points. Now, the reason that I might want to do this is we might realize that if I have a data set with two different classifications, blue and red, maybe later I look at a random point and I want to know, is this going to be blue or is it going to be red? If I just have a line that separates them, I could guess, hey, if you give me a point over here, I notice it's on the red side of the line. Maybe this point would be a red point. And of course, that's where this comes into machine learning, the ability to generalize from some data set you have. If I have some set of points that I can divide between red and blue based on their characteristics, I could then take some new observation and use this as a way of estimating whether it is a red point or a blue point. So this, of course, that's why we're talking about classifiers here. So that's our task. I want to decide if there exists a line such that every point in one set is on one side of the line and every point in the other set is on the other side of the line. And of course, that line may not always exist. Now, this problem is also presented in one of our books, and I do not like the way that they present it. I really don't like it. So when it says a simplification that could be problematic, obviously, that's diplomatic slide talk. What that's referring to is that it appears that what they're trying to do is assume that blue will always, or whatever, that a particular set A or set B, so let's say blue in this case, blue will always be on the left, or blue will always be sort of vaguely up here. And I don't like that. Obviously, I like a problem where we could come in and it could turn out all the red points are over here. I don't want to have to make an assumption that the blue points will always be on one side. There are reasons why this simplification can be remedied. That is to say, you could just try flipping the sets of points. But I feel like it's not as conceptually elegant as just doing it properly. So the way I'm going to present it is what I consider to be doing it properly. It is also the way the Vanderbay book does it. Although I have other disagreements with some of the commentary in the Vanderbay book. So as usual, I'm just going to complain about everything. So obviously, for the sake of a 2D video with 2D slides, I'm going to use the 2D case. However, creating these classifiers, this is a problem of finding, in this case, a separating line, but it would generalize to finding a separating plane or a separating hyperplane. What I really want is a linear function such that everything in set B is, let's say, in this half space, and everything in set A is not. That's really all I'm asking for. And we know that half spaces generalize to any number of dimensions. So it doesn't matter that, like, I'm talking about 2D applications here. This generalizes very easily to 3 dimensions or 4 dimensions. All I'm doing is finding a linear function such that everything in one set is in a half space, defined by that function, and everything else, everything in the other set, is not. Okay, and so, yeah, that's what this is saying. We're finding a separating line or separating plane or separating hyperplane. And of course, this is something that's important in machine learning applications, construction of linear classifiers. And one of the reasons is because evaluating a linear classifier is really easy. If you give me a new point and you tell me that it's here and ask me, do you think this point is red or blue? All I have to do is ask the question, hey, what side of the line is it on? And we know already that's an easy question to ask. And if it's on this side of the line, I say, well, I guess it's a blue point then. That's the guess that I make. And keep in mind that obviously the blue points are sort of clustered around here, but I may make an observation that asks about a point down here or over here. And therefore having this separating line allows me to make that guess regardless. And it turns out, we'll see later, it doesn't even require too much knowledge of the other blue points. I could have 1,000,000 points on each side of the line, and this is in 2 dimensions. If I have 1,000,000 points on each side of the line, comparing my new observation to all of those points could be really difficult. If instead I have this linear classifier that I computed in advance, all I have to do is evaluate one linear function in 2 dimensions, which is pretty easy. So we know a lot about linear functions by now. And we know that if I'm just talking about creating a line such that the blue points are on one side and the red points are on the other, then really what I want to do is I want to find, well, how do we define lines usually? I want to find a normal vector for my line such that if I write the line out in the usual notation that I use, I'm going to use a vector. I'll call it C. So suppose this vector is the vector C. And I'm asking about a particular point. Here's a point P. What I want is, we'll call this point P, and then later I'm going to ask about some new point R. I know that all of the points on this side of the line are the points such that C dot R is less than or equal to some constant D, which is defined based on where the line is. And I know, therefore, that means that if I had this point P over here, that P C dot P is less than or equal to D, and so on. And so similarly, if I look at a point Q on this side of the line, what I want is to also have the property that C dot Q is strictly greater than D. I don't want a situation where I've got both a red point and a blue point that lie on the line. That would be a problem, because then we would be able to confuse them. So what I sort of want is this. I want these strict inequalities. I want no points at all in either set to actually lie on the line. Instead, I want every point in set A to have this property. So I choose some constant vector C and a value D, such that every point in A is on one side, strictly on one side of the line, and every point in B is strictly on the other side of the line. And this actually already looks pretty linear, if you think about it. So what I have is a set of constraints that I've just specified here. This is just a set of constraints. There are a lot of them. There's going to be one constraint for each point in A and one constraint for each point in B. I want to find a vector C and a constant D such that these constraints hold for every point in A and B. The problem is, of course, we don't know what to do with these. We don't know how to handle strict inequalities, and we're not allowed to use them in linear programs, because we've seen earlier that if we define these half spaces that use strict inequalities, we end up with a strange open set, which doesn't actually contain its own boundary, which really makes a mess of things. And of course, keep in mind that the usual way that we solve linear programs is by looking for intersections of half spaces and looking for vertices. A vertex can't exist if we're using strict inequalities. And so we need to somehow find a way to use weak inequalities, to use the less than or equal to sign instead. And in this case, that's a bit of a tough one. But we do actually have a couple of options here. So what we could do is say, look, let's just see what happens if we allow this to be a less than or equal to sign. If we allow some points to actually lie on the line. And we know that if we allow it and we try and run a linear program to solve that, it probably will give us that. The usual problem with linear programming, of course, is you specify an optimization problem, you get back a result that is correct, and you stare at it and say, I don't like this. And that's because you don't always want what you want. If we allow it to do this, it probably will do this, and that might get in our way. But we could try that. That's our first try. So I'm going to construct a linear program with with optimization variables c, which is a vector, so it depends on the number of dimensions we're in, and a constant d. And my constraint system will be that I would like this to hold. So for every point in A, I would like that point to lie on one side of the line. And for every point in B, I want the point to lie on the other side of the line. But in both cases, points are allowed to actually sit on the line itself. And all I need is any line that meets that criteria. So I'm not actually optimizing anything yet. I'm just finding a feasible point. I'm finding any vector C and constant D such that all of these constraints hold. So I'm doing one of these feasibility only cases. And that's sort of nice. Given that I already know that I'm on some thin ice here, allowing points to sit on the line, the fact that I end up with a trivial objective function is sort of good because it means that I have a lot of room to move later. If I just find an objective function, maybe I can find some way of keeping those points away from the line. So I end up, let's say, with this. If I solve that optimization problem, I might end up with this line here. Because the points in each set are actually allowed to be on the line, here I have this separating line where two of the red points are actually sitting on the line itself. But the constraints are all met. Everything that's red is either on the line or on this side of the line, and everything that's blue is either on the line or on this side of the line. But I stare at this and notice, there are a lot of better choices for a line. I mean, I could have chosen, this line here. I could have chosen something like that. There are plenty of other choices, and in fact, in particular, there's probably a line that sits right in the middle, where the distance from the line to any point in either set is pretty large, and I like that. I like the idea that just in case there needs to be a margin of error, it's as big as possible. Because that way, if you ask me about an observation sort of here, I'm more likely to be accurate. And for an example of that, think about this. If I make an observation and I say, hey, this point here, is this point red or blue, more likely? And according to the current separator, the point should be blue. It's on the blue side of the line. But is it really more likely to be blue than red? It looks like it's a lot closer to some red points than some blue points, if we think about it. So this separator line isn't ideal. It doesn't seem to, although it does separate the two sets, barely, it doesn't seem to provide us the best possible estimate. I would argue that everything that's relatively close, everything about here, all of this stuff, that's probably more likely to be red than blue. So what I probably want, given that there are clearly there are multiple choices for lines, I probably want a line that runs right down the middle, that separates the two sets and keeps as much distance as possible between either set and the line. So what do I do? And here's another example. If I solve it for this particular case, it does give me a line that lies between the two sets, but notice how the line is still quite a bit closer to blue than it is to red. And we could argue that if I look at this point here, even though it's on the red side of the line, it might well be more of a blue point, really. It's more likely to be blue than red. And so we want some way of optimizing the line. We know that there could be lots of different choices. I want to find the one that provides me the largest margin on either side. Now, on the other hand, if this LP were to be infeasible, that would mean that there is no line that meets the criteria. And of course, that would mean there is no way of separating these two sets of points with a linear function. So we already do have a way to decide if the line exists or not. But what we want is, if the line exists, certainly we still want to know whether it's infeasible. But if the line exists, I want the line that maximizes the distance from the line to any point in either set. And of course, we know already from the previous case that when I say that maximize the distance to any point, what I really care about is the closest point, because clearly the distance to the closest point will be less than the distance to any other point. I want something like this. I want to have the largest margin of error between the line and either side of the line, so the red points and the blue ones. So let's try this. I know that I don't have an objective function. So I have this LP that gives me a line, but it has no objective function. Maybe I just, now that I know there are multiple solutions, I could use the objective function to choose a better one. So what I'll do is I'll think, okay, is there a way to consider this margin of error, which I've called epsilon here, and I'm actually not going to call it that in the coming examples because there is a tiny semantic problem that I'll get to later. But I'll try and find a way of representing this distance, the distance from the line to the nearest point on either side. And I want to make that distance as large as possible. So I want to maximize, we'll call it Q in this case. I want to maximize my value Q such that everything on, nope, not such that, subject to the constraints that every point in set A lies on one side of the line, but offset by distance Q. So what I'm really saying there is I want to create my central line, and then I want to have this other line here, which is sort of the line D minus Q, and then there's D plus Q. And I want everything in the blue set to lie on this side of the line D minus Q, and everything in the red set to lie on this side of the line D plus Q. So I'm actually deliberately defining, quite literally, a gray area where no points are allowed to be. Nothing is allowed to lie between these offset lines and the line itself. And I want to find the largest Q that I can. I want to make the gray area as wide as possible. So I do this. So I maximize Q such that everything in set A lies on one side of the line defined by D minus Q, and everything in set B lies on the other side of the line defined by D plus Q. And the idea is I want to find a normal vector C and this offset Q that is as big as possible. In this case, just like before, if I find out that the LP is infeasible, then there is, if the LP is completely infeasible, even with Q equal to 0, then that means there's no way to draw the line to begin with no gray area. On the other hand, if the LP is feasible but the optimal value of Q equals 0, then I've got a problem where I can probably draw it out here. In that case, they're not fully separable because that would be a situation if Q has to equal 0. It means that there is no line that builds in any margin at all between red and blue. So an example would be a case where this is supposed to be blue, but where one of the round points actually lies on the separating line, as does the square point. Remember that our original objective was to make it so that every point on either side is strictly away from the line, that nothing is lying on the line itself. And we know that we can't do strict inequalities, but it turns out this allows us to get the same effect. If Q ends up being equal to 0, that means we didn't get the strict inequality that we wanted. That means we ended up with a weak inequality, which is undesirable. So this actually allows us to simulate a strict inequality by using this proxy variable Q. And so if Q ends up equaling 0, then the strict inequalities are not being met, and therefore there is no separating plane. But there is still a problem, which is that we're trying to maximize this value Q, this new variable I introduced. And you'll notice that, of course, I'm maximizing it, okay, but I've also added it to both sides of everything. And you'll notice the sign is different, minus Q plus Q, but you'll also notice that because the inequalities are different, these will both end up having the same sign on Q once I convert to standard form. And this results in quite a problem. Because it means if I find any feasible solution, so the optimization variables are the C's and D and Q. If I find any feasible solution, an arbitrary multiple of that solution will also be a feasible solution. And that's not normally a problem, except for the fact that I'm maximizing Q. So if I can multiply the solution by any positive value and get an equally valid solution, the problem is just going to be unbounded. Always. Pretty much. And that's not acceptable. We have to find some way of keeping the problem under control. And to be clear, the reason the problem is unbounded has nothing to do with the application. It's just a consequence of the fact that there are too many variables, basically. There are not enough restrictions. So I have this normal vector C, and that's one of my optimization variables. And we know that a normal vector's length is irrelevant to us usually. All we care about is its direction. And the problem is, because of the way I'm specifying it, there are no constraints on the length of my normal vector. It can be as long as I want. And that means that when I'm maximizing Q, if I multiply everything, including the length of my normal vector, by this constant, I can make Q as big as I want. And that results in the problem being unbounded. The solution is to find some way of restricting how big the magnitude of my normal vector can be. because that would mean that I can't just take an arbitrary multiple of my vector c and have it continue to be feasible. And it turns out that that's where we end up with a little bit of a problem with linear programming. So I could try this. I could say, well, to avoid arbitrarily scaling a feasible solution, what I can do is restrict the magnitude of some variables. And it turns out that I can't really restrict the magnitude of q or d. I don't want to restrict the magnitude of q because I'm optimized. I want to maximize q. And I can't restrict d for a couple of other reasons. But I can restrict the magnitude of my vector c, of all these coefficients c1 to cn. And if I do that, that will be enough to stop me from scaling an entire feasible solution. I'm only allowed to scale my feasible solution if I apply the same scale factor to literally everything. So if I restrict any of these variables, that'll be enough to stop the problem from going to infinity. And so to do that, what I could do is just say, let's demand that c be a unit vector. Because c is supposed to be the normal vector to my line. And I obviously don't care how long the vector is. Let's deliberately prevent that from being anything but a unit vector. And the reason why that's helpful is that I can observe that it's really easy to add that. Because if I have this constraint here, and I know that the length of a vector is always positive, then this follows. I'm not changing anything by dividing both sides by the length of c. So what I could do is observe that this is equivalent to me just demanding that c itself is a unit vector all along. So if c is an arbitrary vector, this constraint is equivalent to this one. But that means that arguably I don't need c to be an arbitrary vector. I can just have c be a unit vector. And therefore, if I restrict c to being unit vectors, I prohibit this particular arbitrary scaling that's causing me all sorts of trouble. On the other hand, how do I make c, which is a vector that is one of my optimization variables, how do I make that a unit vector? Well, I could add a constraint like this, which is, of course, really, really nonlinear. So I can't do that in an LP. I just don't have that as an option. So what do? Okay, one option is I could write a quadratic program. I could forfeit the linearity of the problem, and I could hope that I can find a solver for quadratic programming. And it turns out that, generally speaking, quadratic programming is considered pretty much just one step up from linear programming, and then one step above that would be arbitrary convex programming. And it turns out that there are indeed plenty of algorithms for quadratic programming that are pretty good. There are, in fact, some that are based on the simplex method, which is sort of unusual because the simplex method is so inherently linear. There are also lots of interior point solvers for linear programs that also work pretty well for quadratic ones because quadratic functions are actually pretty well behaved. And so if I do that, I still don't want to use square roots. I don't want to have a constraint about square roots, but we know that we can constrain the length of a vector by constraining the square of the length of the vector. So we could just have this constraint, which is a quadratic constraint. But this is a course in linear programming, so give me a break. What are we supposed to do? Speaking of which, there is a course offered in the fall about convex programming, so it's worth considering that you might want to take that course if you're still interested in optimization after all this. But is there a way to solve this with a linear program? And yes, the answer is yes, but it requires us to sacrifice a bit of accuracy. So what I could do is I could say I can't force c to be formally a unit vector, because that would require me to impose constraints on its length, which is quadratic. What I could do, though, is I could say, let's just require that each component of c be between -1 and 1. Certainly, that'll prevent me from scaling c to some massive positive or negative value. Certainly, it'll prevent that. Why don't I just restrict each component ci to have a magnitude less than or equal to 1? That will mean that c could be a non-unit vector in some cases, but it will not allow c to be scaled arbitrarily. And so I end up with this linear program here. And this will compute a classifier. Now, there are cases where this will not compute the absolute best classifier. And I'm actually interested myself. I'm going to talk about this in a live session. I'm interested myself in knowing whether or not making the sets of points big enough actually does ensure that the answers will match between both. I can think of a couple of counterexamples in very small cases, in cases where there are very few points in each set and therefore a lot of variability, a lot of possible solutions for the line. My general thought is that the more points I have, the fewer choices there really are for the direction of the line. And therefore, that is to say, if I have enough points and they're positioned in general position, it turns out any possible separating plane pretty much has to have a certain direction. And therefore, the only real variable is that margin as opposed to the direction. C only dictates the direction, but I believe it to be the case, certainly, that if we're not restricting C to be a unit vector, there could be ways of coming up with a suboptimal solution if there are a very small number of points on each side. side, and they have certain geometric relationships. So formally, we cannot completely simulate this constraint with a linear program, but according to people like Vanderbay, it appears as if, in general, when you have large sets of points, not only is this a good enough approximation, but it's likely to match the optimal solution in many cases anyway. And so we end up with this, which is a linear program. And maybe it doesn't surprise us too much that we can get a linear program out of this because it was a fundamentally very linear problem. Find a linear function, here's our linear function, find a linear function such that all of the points in one set are in one half space and all of the points in the other set lie in the other half space on the other side of the linear function. Fair enough. That's why we could derive a linear classifier. And so the final LP that I just showed there will produce a line with the maximum margin between each point set according to, assuming we sort of accept the compromise that we had to make about how distance is measured. So we end up with this and we end up with this, and you can see those are pretty good results using that linear program. It's also worth noticing that you might have heard the term support vector machine, either in the world at large or in a machine learning course, to refer to cases where a linear classifier is used to distinguish between points on either side of a line or a half space. And the term support vector comes from the fact that if you look at this for a while, you might notice that really the whole line, everything is defined by these points that are closest to the line. This and this and this and these things don't factor in at all. The direction of the line and the margin between the line and the points is pretty much entirely defined by these set of points on either side that are closest to the line. It's also true that we can expect, of course, that the distance between the closest red point on the line will equal the distance between the closest blue point on the line, because if not, we could move the line a bit and get a better solution. So the term support vector comes from the fact that these points here, the ones that dictate the position of the line, are sort of, they support the line. They support the separating hyperplane. And the other points actually have no bearing at all. So what's really exciting about this, I mean, this is obviously an interesting application because we're dragging machine learning into something and it's 2021. But what's really interesting about this is the fact that I mentioned a minute ago, oh yeah, of course this was a linear application. We're making a linear function with a set of points and we're working with half spaces. What's really bizarre is that we can use the exact same logic for non-linear functions, which is actually, I think, an astounding result. Because if we think about what we really did, we came up with some coefficients for what happened to be a linear function. We used linear programming an optimization strategy that found coefficients on some function, which happened to be a linear function. But what's stopping us from looking for the coefficients for a nonlinear function? So here's an example where there is no separating plane. There's nowhere I can draw a line that will separate the blue from the red. On the other hand, I could draw something that separates blue from red. So I could draw a circle or an ellipse. So here's an example. I could come up with a quadratic function that separates the two sets. And what I mean by that is that, let's see, so what I want is something, an arbitrary function f, such that f of xy is less than c for all points xy in set A, and f of xy is greater, just greater than c for all xy in B. And we can think about this as sort of dividing as this location C, or in general the curve, I'll draw it this way. This curve here that defines the separator, this is just going to be the level curve f of xy equals c. Every location where f of xy is less than c, that puts us in blue land. Every location where f of xy is greater than c puts us in red land. So it turns out that there is a way of separating red from blue. The question is, how do I get this function f of xy? And in this case, we know it's a quadratic function because it's an ellipse. We do have to know in advance what degree of polynomial we need, but we're not restricted to quadratic functions. It gets pretty unpleasant to look at, but we can do this with cubic functions or functions of higher degree as well, as long as we know in advance what degree we need. And so really what we just did with linear classification was this. It was given some abstraction of a function, so we need coefficients on some function, which is formed by a linear combination of things. Whether or not those be linear things, we would like to find these coefficients such that we get this property, such that these constraints are observed. And now, if we think about the most abstract version of a quadratic function, so here's a quadratic function on x and y. And I have written in every possible term that could exist on a two-variable polynomial on x and y with degree 2. It's a quadratic, which is a times x squared plus b times y squared plus the term of x times y plus something times x plus something times y plus a constant. That's all you could. Ultimately, any two-variable quadratic function can be turned into this. It can be expanded out to something of this form with all these coefficients: a, b, r, s, t, and c. And it was a bit of a challenge when I made these slides to come up with good names for them. As in the case of a linear classifier, obviously the values of x and y are provided, when I'm considering these constraints, the values of x and y are constants provided by these input sets. And therefore, if I want to talk about x squared for a particular value, a particular point xy, well, the point itself is constant. It's part of this input set, A or input set B. So if I want to compute x squared, I could do that in advance. Just like before, where I was able to compute square roots as long as I did it as part of preprocessing. So I could construct a linear program to find the best coefficients and, of course, our margin Q such that these constraints are obeyed. All I have to do is take each point xy and compute x squared and y squared and encode them into the constraint system. And notice that if I do that, all of the things I'm looking for, the coefficients a, b, r, s, t, and c, those themselves are actually a linear combination. They're a linear function where they're being multiplied by these constants. And so although I'm working with a nonlinear function, I'm not working with it in a nonlinear way. And so in this case, an ellipse can be characterized by a quadratic equation. And so I would, if I solve the linear program I just described, I would end up with this function here. This is just a plot of the function in general. And if I choose this particular level curve, the one for the constant d, which is one of the optimization variables, I get this. And everything with f of xy is being less than d minus q are in set A, and everything in set B will have f of xy is greater than or equal to d plus q. And so just like before, I'm even able to get the best margin. I'm able to get an ellipse that separates the points from the curve by as large a distance as possible. And due to the number of coefficients, I mean the fact that I'm optimizing something with all of these coefficients, I am able to obtain all sorts of strange curve shapes, pretty much any quadratic function, which, as you might remember from like grade 10 or something, is a conic section. And so I could end up with a circle, I could end up with an ellipse, I could end up with a hyperbola, which I think is what we have here. I could end up with a parabola. But I can find a way of separating these sets of points, and I could actually do this again with cubic functions or higher degree polynomials if I needed to. I can derive these non-linear classifiers using linear programming, because as far as deriving the coefficients goes, that itself is a linear problem. And this is actually similar to the fact if you've taken numerical analysis, and we're going to come back to this later in this course, you might have seen things like interpolation with polynomials, and how you could compute an interpolating polynomial, the coefficients for that, by working with matrices, working with linear algebra, even though the polynomial itself is, of course, nonlinear. And so we end up, and this is an example where it's a really weird-looking wide ellipse. Okay, so those are our two applications for this week. Two cases where we're working with things that are fundamentally nice 2D geometry applications as we specified them. They work in higher dimensions as well. Points and polygons, but where weird nonlinear stuff shows up. But we are able to find a way of removing all the nonlinearity before solving the optimization problem. And so we can turn what turns out to be a nonlinear application into a linear optimization problem.